So today I will be talking about some of the work that we are doing at our lab, which mainly revolves around how we can use deep learning, how we can enhance deep learning for uh, making better predictions in a data efficient manner where the positive cases are very less or less. So uh, I will be talking about how we can use federated learning, information transfer, multitasking, and in terms of the optimization landscape, I'll try to bridge all of them together. They are essentially the same thing, doing the same thing with different aspects. And why do we need them to tackle the theme of today's event, that is handling rare events. So when we talk about the rare events or the lesser data in training, like lesser positive data in training, the biggest challenge here is when we try to train a bigger model, a neural network, essentially, we suffer from overfitting and lesser generalization. We all know this thing. This is nothing new here. The problem is, why is that the issue? The issue is simplicity bias, which has been recently analyzed issue in deep learning. So in one sense, what we can see is, let's say that we have two samples of a positive disease prediction. So when we are training our model, they are only looking at these two dynamics. So when the third one comes up, even our model is very strong enough, it cannot capture that. It says that I don't know how to do it. That is a reasonable thing to predict, but still, like, we can make certain changes to our modeling, to our optimization, to make sure that the model have to work harder to learn some semantic characteristics in the underlying optimization issue. So how do we overcome these issues of data rarity? So first thing first is information sharing. We all know information sharing. That is transfer learning, multitasking, meta learning. And then there is a slightly new phenomena, that is data democratization. So as Sir pointed out, that due to data regulations, it's not very easy to make the data sets available to everyone. And I work in UK, so we have different NHS trusts. Each NHS trust is essentially a different organization. So within England, I cannot ask other NHS trusts to give me data. So that basically means that the bureaucracy, and the right word would be regulations, is in place for preventing data privacy. So how we can use AI, machine learning, not to overcome these obstacles, but how to work within the frameworks of the privacy and still be able to share the data. And then there is federated learning, which somehow lies between the two. We do information sharing, and at the same time, we are somehow able to train our models in a distributed manner so that we don't have to collect the data at the same site. So first, I will take just few seconds to revisit multitasking so that we can cover everything together in terms of the federated learning. So in multitasking, we have one example and multiple labels, and each label corresponds to one task. So when we train our model, what we do, we compute our losses. For each task, we compute the loss. We do some linear combination of those losses, and then we compute the gradient of this aggregated loss, and that we use that aggregated gradient or aggregated gradient that is computed from aggregated loss to update our model. So what does it look like at the back end? So an illustration here is, for example, we are dealing with 4 tasks, and the optimum parameters of each of these tasks is theta 1, theta 2, theta 3, theta 4. When we do multitasking and when we aggregate the gradients or aggregate the losses, we get something that is theta, that is red in color, which basically means that we try to find a point that is equidistant, if we are talking about the convex combination in terms of the losses, from each of the optima. So in essence, we are not learning the optimum thing for every task, but we are learning the optima that is closest to everything. So this is the reason why we get less overfitting when we go for multitasking. In terms of the meta learning, the gradient-based meta learning, first order meta learning, whether it is reptile or whether it is MAML, The optimization is somewhat similar. So what we do in meta learning, we have shared parameters. In each iteration, what we do, we take these shared parameter and we ask each of the tasks to update these parameters using its data. So theta becomes theta dash. So what we do, we subtract theta from theta dash, and that becomes our gradient for a task. Then what we do, we aggregate these gradients, and in the same way, we train our shared model, we update our shared model. So in essence, whether you aggregate the loss and compute the gradients, or you compute the gradients and aggregate them together, in essence, from an optimization standpoint, this is the same thing. And this is what we do in federated learning as well, which we will see. Okay. So a bit of, after this background in multitasking or transfer learning, how many of you have used transfer learning and witnessed that it works in non-imaging tasks specifically? In what scenarios?
Time series there.
Okay.
On mobile and everything.
Okay. So ideally, if you do, in my experience, I've done it a lot. If you do 10 tasks, 10 random tasks and try to do transfer learning or train them together, 90% of the time it won't work as well as. And there is a reason for that. When we try to group similar tasks for multitasking, what do we think? We try to look for the semantics from the human standpoint. For example, okay, mortality and decompensation should be grouped together because they're kind of the same thing. Like mortality, decompensation signals mortality. Mortality won't happen until there is decompensation, deterioration in patient condition, nice, right? So they seem similar. But the problem is when you try to do them together, especially on Mimic, you will see that it is not just dependent on the task similarity. It is also dependent on your architecture. It is dependent on your optimization landscape, your optimization algorithms, and everything. So one of the biggest challenge in multitasking literature is how we can find the task which we can train together, which essentially translates to what pre-training model should I choose for my downstream task. Pre-training downstream task is easier because you don't have to do joint optimization. So we can give it a rest a bit, but still, it's the same principles. So in our work, what we are trying to do is we try to find out which tasks should be grouped together or should be trained together in a multitasking framework. So look at this figure, and this is a classical mimic 3 tasks, which we have mortality prediction, phenotyping, and decompensation prediction. So some of the people from our lab, they used to train a multitasking model for all 3 of these tasks, whether using multitasking or whether using meta learning. But what most of them found out was it wasn't feasible to get better performance on all 3 of the tasks. Sometimes mortality was better, sometimes phenotyping was better, but all of them, single tasking was still better. Then we analyzed the gradients and found that for some scenarios, for some tasks, these gradients are conflicting each other, which we know as negative transfer. So if the tasks are not synchronized together, they are not behaving similarly in terms of gradients, what will happen? Their optimas will lie far away. And when the average is there, so average is not good for this task, average is not good for the other task. So in essence, multitasking is not the right solution. And the whole multitasking literature has only worked on how we can avoid this negative transfer. So rather than dealing with negative transfer, this work tries to avoid it altogether. We want to find the tasks which don't show any negative transfer. So before our work, there were only 2 or 3 of these papers were out there who have addressed this problem. Most of them were computationally extremely expensive. As a result, like it was easier to train models on all the permutations and combinations of the task rather than trying to find the complexity, trying to find the ideal task grouping. So in our work, what we do is we use sample-wise optima. So before training the model itself, we try to predict, okay, which of these tasks could be trained together in a very computationally efficient manner. Did I do something? Okay. So before So before presenting our very intuitive technique, I just want to highlight some of the nomenclature that I will be using. So the scenario is same. We have a neural network that is parameterized by shared parameters theta. It is initialized randomly. The parameters are given by theta 0. And we have an ith sample of a multitasking data set. What we do, we take one sample and we train this model. We update this model, theta 0 to theta dash. What we call this thing, theta it star, the sample-wise task-specific optima. For all the tasks that are there for the ith sample, we aggregate these optimas and we get sample-wise optima. So these two statements are clear? Okay. So now I want you to analyze this picture. So this basically tells us the loss landscape, the loss curves of two tasks whose losses are given by L1 and L2. So first scenario is where the task-specific optimas are far away from each other. So obviously, as they are far away from each other, their average is giving us the higher joint loss, both L1 and L2. On the other hand, when we are talking about the denser optima, the average point, the sample-wise optima, is closer to all of them. So that basically means that we will get the lower joint loss. So in essence, this provides us some intuition about the training loss of multitasking setup without actually training the model. So I won't bore you with some mathematical details, but in essence, it shows that if the density of the sample-wise optima on the training data set is less, which means that, density is high, which means that distance between all these optima is less, your training loss will be less, which basically means that there is a positive transfer and lesser negative transfer. So what we can do is, we can just sample some data set, some samples from our data set for different tasks, like just pass them through our formulation, get the optimas, and compare the distance between the optimas. We can get an intuition whether these tasks should be trained together or not. So this is one example that we have. I'm not sure it is too visible, but there are optimas that are obtained for ResNet 50, and three data sets that we are dealing with is CIFAR10, SVNH, Street View house numbers, and colorectal histology data sets, which is tissue images. So the 2 points which are close to each other are CIFAR and SVNH, which are shorter natural images, and the other ones, which are the green ones, are far away from these two things, which are our tissue images, which in essence, this makes sense because tissue images are way more different than the other images. So this is proof of concept of our method that it works fine. So moving on to the federated learning. So why I covered that, sorry, I may have forgotten to mix that. So when we are going for transfer learning or multitasking for any of our rare disease prediction tasks, if we have to identify the diseases that we can leverage or we can share some information from, we need to be very careful what we choose. And it is good to do this sort of analysis and make an informative prediction rather than just doing it hit and try. So the other phenomena that I wanted to cover was federated learning. So in federated learning, it's basically distributed training of our models. So we have clients, which can be our medical institutions. They have their own data. And we want to learn a model which is a function of all of these clients without taking their data outside of their jurisdiction. So in federated learning, the idea is very simple. There is a server which is a centralized authority that wants to train the model. It will initialize the model parameter and model definition, and it will send it to each of the client. The client will update the model, and it will send back it to the server. Server will aggregate it, and this will go on again and again and again. So in no time, your server, your data is leaving the client's data framework. So in this way, without violating the privacy, we can obtain these kind of models. So one very good example is during COVID time, our lab have created a Curial data set and Curial model that works across 4 different NHS trusts. We got all the permissions in place, and we trained in a real world how we can implement federated learning for healthcare scenarios, which was one of the, I guess, Europe's first model, if not world's first model, on non-imaging things. Like on imaging, it's easier. On non-imaging, this problem becomes extremely difficult because we have to make a lot of assumption. So if you're talking about the tabular data, assume the assumption is the distribution of data is the same, the number of features that are available across each sites are same, they are standardized, and the location of feature is also same in the feature vector, which is obviously, when we worked on this, we realized that this is not true. And we spent like 6 months just to standardize the data. Yeah. So in next work, what we tried to do is we tried to train the federated learning model that can work across data view heterogeneity. It is different from the heterogeneity that Professor mentioned earlier. We are not talking about the distribution shifts. We are talking about at some sites there are no features. For example, at one site the dimensionality of feature is 10, at other side its dimensionality is 20. So what we do, we first learn, we use something called knowledge filtering module, which is you develop a knowledge vector, you train a knowledge vector during the federated training, and you use this federated model to project the input data to a semantic space, and you train your model on the semantic space. And the results of this work were like kind of mind-blowing, that in case of feature disparity and in case of shuffled data views, our framework outperformed all the available baselines, even the standardized models. We showed that it works well. I have data set condensation as well, but I will just leave it here. In case you want to discuss this further, please let me know. Okay. Thank you.